thank you so much for having me here. I'm presenting a work that we conducted originally for ICR, but I'm very glad that I can share this with you guys here today as well, because it's a benchmarking paper of maximum independent set solvers. And we basically went ahead in a seminar, so I'm a master student at HPI, and went ahead and re-implemented some well-cited, well-known methods in deep learning for combinatorial optimization, and got some interesting findings out of it. So this was joint work together with Otto, Martin, Sarel, Cohen, and Tobias. And yeah, what the core takeaway of this will be is that you should really dive deep into evaluation and isolate what really the machine learning part of a solver is and what all the other engineering techniques that you do are, because in the end you want to say be improved upon the state of the art using some machine learning techniques. So but to get started with, let's discuss first what an independent set actually is. And by definition, an independent set is a set of non-adjacent vertices in a graph. So if you take a look on the graph here on the left side of the slide, you can basically see blue vertices and black vertices. And you notice that all the blue vertices are not connected. So they are not neighbored, non-adjacent. And this means they form an independent set. Also, you could say each vertex on its own forms an independent set. And also the empty set is an independent set. And therefore, we are interested in finding the largest one. Unfortunately, this is quite sad because it's NP hard. So we have to be smart about it and find a way on still finding the maximum independent set without enumerating all solutions. And one algorithm that the ML community especially has discussed in the context of this is the tree search algorithm. And you can think of it as a smart brute force. So if you consider the graph you can see here on the left side, we start out with this graph, and now somehow we want to be able to find a maximum independent set. What we do here is we label the vertices as part of the independent set. So this is the blue color, and is not part of the independent set. This is the orange color. For vertices where we didn't decide yet, they are grayed out. So now the core idea is that we can somehow call somebody or query an oracle, and this guy will tell us, okay, with probability 85%, the upper left vertex will belong to our solution. So just assume for now that we have access to this oracle, and we obtain the probabilities as you can see on the screen right now. Then one very simple approach is to go ahead and say, okay, because the vertex on the upper left side has the highest probability of belonging to any solution, let's take it into our set, into our maximum independent set, because probably it will be a good vertex for us. And then by definition, we have to mark its neighbor as not part of the solution. And now we can go ahead and repetitively, basically greedily iterate over our graph and take these vertices. So 76 is the next highest probability, and therefore we have to take its neighbors as not part of the solution. And then last, we can take the upper right vertex as part of the solution again. And now this is all good. We found a maximum independent set. But the question is, how do we get this oracle? How do we get the probability information? And one way of solving this is using a graph neural network as an oracle. And this was like at NeurIPS 2018 already an idea that Lee et al. Had. And it was quite revolutionary paper, I would say, at that time for combinatorial optimization, where basically we train a graph neural network on maximum independent set instances and then expect to get some probabilities for the tree search algorithm. And this is how the pipeline looked like in the paper. So they took a graph, they reduced it to a smaller graph. So basically you can apply some algorithm engineering techniques and then show, okay, these vertices basically have to belong to our solution, or they provably are not part of our solution. And then with this reduced graph where we cannot make any concrete statements yet, we take it into a graph convolutional network, so multiple layers. And then based on the probabilities that this neural network outputs, we perform the tree search as I've just discussed. And note that we basically also take multiple outputs. So we maintain a diverse set of solutions. And then each time we finalize the labeling of a graph, we perform a locus search. A locus search is basically an evolutionary algorithm. mutates, does some local mutations in evolutionary algorithm, has some other techniques, but you can think of it as an evolutionary optimization. And then we just choose the best out of these techniques. And what I want you to focus on is the graph reduction and the locus search, because these are two techniques that are there in the pipeline, but they surround the GCN. And now the question is, if we get good independent sets out of it, what is actually causing the good solutions? And what we find is that baselines are important. So what you can see here on the screen is multiple data sets. So we find Erdős-Rini graphs, random graphs, hyperbolic random graphs, and 2 benchmark data sets. And you can see the average size as a viable plot of the maximum independent set of these graph data sets for different solvers. And if you focus on the last column in each plot, this is a column where we replace the neural network by random noise. So as you can see, there's no noticeable difference, for example, between the first and the last column. And this already is like the nutshell insight of our paper. In this pipeline that has been cited like 200 times or maybe 300 times by now, the neural network is not actually doing any work. It's the techniques that algorithm engineers and also like locus search optimization people have been discussing for quite some time now, and we can just replace our neural network by random noise without gaining or losing performance in our solvers. So this is like the first insight we got. The GCN can be replaced with random noise without performance impact. So it's really important to, when proposing such a technique, to have a good baseline and to thoroughly evaluate your method. Of course, we also went ahead and compared it to other solvers that have been published. So we, for example, discussed a reinforcement learning-based solver, called Learning What to Defer. It was published at ICML. And also, for example, Gurobi in various configurations as an ILP solver. And what's maybe also interesting for you is that we bundle all this up. So all the random graphs you see, the real world graphs you see, all the benchmark data sets in one single Python package or framework. So if you come up with a new fancy method for solving maximum independent set, we can hopefully have like a clearer baseline now and compare it to other solvers, so that it's not like this mess that we see or that we have found when we try to reobtain the results. If you want to take a look at the code, there's a QR code here. You can also follow to our GitHub here. We are always open to integrate more solvers. And with that, this concludes the talk. So thank you so much for your attention, and I'm open to any questions.
So what does the machine learning community think about your paper?
Yeah. So is it ICLR, is that it?
Yeah, it was at ICLR, like a large machine learning venue. I didn't really get the question though, sorry.
So the question was, what was the reaction from the machine learning community?
I mean, it actually really depends on the people you were talking to. So we tried to get in contact with the authors of the original paper. And when we got to the point where we said we cannot reproduce this, then the contact just dropped. But in general, I mean, people are always happy if you again challenge the state of the art, it's actual state of the art, and provide open source code. So I guess the reviews were good. So people like the open source approach, but of course they also wanted to see okay, but how can we use machine learning or deep learning, especially now, in a way that actually benefits these techniques. And for this, what was really interesting for us is that reinforcement learning compared to the supervised approach here really improved the results.
Any other questions? No, okay, well, thank you again, and thank you for attending. This concludes the session.
Thank you so much.